Okay, so just we have seen that carbanions, sp hybridized carbanions, they are most stable. Then sp2 hybridized carbanion and sp3 hybridized carbanion is least stable. So this is totally opposite to the carbocation stability. Okay, so carbocation stability and carbanion stability, they are totally opposite to each other. So you can see over here in this slide, sp hybridized carbanion, sp hybridized carbanion are most stable, whereas sp hybridized carbocations, they are least stable. Okay, so these two, the stability of these two reactive intermediates, they are totally opposite to each other. So this is the very important point we have to be we should have taken into consideration. Okay, next effect. Okay, what inductive effect? Now what is the second effect which give the stability to the carbanion? So electron withdrawing groups, like inductive effects, if electron withdrawing groups are present on the carbanion, that means the center, carbanionic center, next to the carbanionic center, adjacent on adjacent carbon atom, if electron withdrawing group is present, or on the that same carbon atom, if electron withdrawing groups are present, then how those things, inductive effect, whether that was plus I inductive effect or minus I inductive effect, how they works on these things, we will see in this slide. Okay, so electron withdrawing groups stabilize negative charge. Okay, so the negative charge is stabilized by adjacent electron withdrawing groups, inductive effects. Okay, so here you can see, if three chlorines, if three electron, these are electron unstable, no electron withdrawing groups are present over on this methane carbanion. Okay, methane carbanion, there is no electron withdrawing groups are present. And if we will increase the electron withdrawing groups one by one, in this one, first one electron withdrawing group present, the stability is increasing, two electron withdrawing groups, and finally three electron withdrawing groups are present there, then that carbanion is the most stable. So minus I effect, electron withdrawing groups minus I effect in increases the stability of the carbanion. Okay, so a negative charge that is adjacent to an atom with electron withdrawing groups on it will be much more stable than an equivalent atom that is not. Okay, so in the extreme case, CCl3, the most resulting ion in many orders of magnitude more stable than the methyl anion itself. Okay, so this is the basis of haloform reaction. So haloform reaction we will see in our coming lectures. We have that name reaction. Okay, so the minus I effect affects the stability of the carbanion. Just we have seen presence of electron withdrawing groups. The electron withdrawing groups like my iodine, fluorine, nitro group will increases the stability of the carbanion. So same thing, the same case like trichlorocarbanion and here trifluorocarbanion. So the trifluorocarbanion is the most stable compared to the methyl carbanion, then monofluorocarbanion, difluorocarbanion, and this one is the trifluorocarbanion. So and in this one is the most stable in case of electron withdrawing group. And if plus I effect is present on the carbanion, plus I effect, if electron donating groups are present, if present effect, electron withdrawing groups like iodine, fluorine, nitro group, cyano group, they increases the stability of that particular carbanion. And electron donating groups like alkyl groups, they do decrease the stability of the carbanion. Here are, I have taken the examples of methyl groups. Here the primary methyl group, secondary methyl groups. Okay, secondary carbanion, sorry, primary carbanion, secondary carbanion, two methyl groups attached. And if three methyl groups attached, electron donating plus I effect is there, then its stability of that particular carbanion is very low. And if one methyl group is present, so that carbanion, that carbon possessing negative, that is the most stable compared to the 2-methyl groups and 3-methyl groups if present on that carbon atom, carbon negative charge holding carbon atom. So, and these are the thing. Minus I effect increases the stability of the carbanion, and plus I effect decreases the stability of the carbanion. Okay, so this is the second factor which we can apply for the stability of the carbanion. First factor, hybridization leads to the stability of different carbanions, and second factor is inductive effect of the different inductive plus I effect and minus I effect, how that one is defines the stability of the carbanion. Now next, as we have compared in case of carbocation and carbanion, here also we will compare the stability of the carbocation and carbanion and electron donating groups, so plus I effect. So in case of carbocation, this is also here also the effect is reverse in case of carbocation and carbanion. If electron donating groups are present, then tertiary carbocation is the most stable. Here electron plus I effect, electron donating groups are present, then tertiary carbocation is the most stable. And if you will see over here, if electron donating plus I effects, the groups which are donating electrons if present on the carbanion, then this carbanion is the least stable. Okay, so the same thing we have observed in hybridization, sp3 sp2 sp, and the same thing observed the same comparison we have observed over here in case of inductive effects. Okay, so the carbocations and carbanions, they do show totally opposite effects with each other. Okay, so in case of carbocations, plus I effects increases the stability, and in case of carbanions, plus I effect decreases the stability. Okay, third point. Now the resonance. Third point is resonance, and we will see now how resonance stabilizes the carbanion, or how resonance helps to stabilize the carbanion. Okay, how the resonance increases the stability of the carbanion. Okay, negative charge, stabilization of negative charge. So the negative charge that is adjacent to one or more pi bond. Okay, so one or more pi bonds can disperse its negative charge over multiple atoms. So as we have discussed earlier that for carbocations as well as for carbanions, if we are able to delocalize that positive charge or negative charge on different atoms, so that atom, so that charge, whether that one positive charge or negative charge, is getting more happy as that one is delocalizing on different atoms. So in that way, by delocalization, that one is gaining more and more stability. Okay, so if negative charge is in conjugation with the double bonds, then these negative charge, that one is getting delocalized on different carbon atoms by shifting these lone pairs and these double bonds. So there is shifting of these lone pairs in conjugation with this carbon carbon double bond. Okay, so these, in this way we can say that one is resonance. Okay, resonance occurs, or we can say this negative charge is delocalizing from one atom to another atom to another. So that one is jumping from one atom to another atom, from one home to another home. Okay, so this jumping from one home to another home, it imparts stability to that carbanion. Okay, so this is the third point. Resonance is giving stabilization to the negative charge. For this resonance, we must have the carbon carbon double bond is in conjugation to that negative charge. So conjugation is important. Conjugation, carbon carbon double bond should be in conjugation with the this negative charge, and that after delocalization of this negative charge, after shifting of this carbon carbon double bond, we can give the more stability to this negative charge. So this is nothing but the resonance effect. And resonance effect we can see in case of phenyl, that means benzyl carbanion. So here you can see benzyl group is here, C6H5 CH2 minus. So this benzyl group, negative charge is residing on the CH2, and this negative charge is delocalizing now over all these 6 carbon atom of benzene ring. Okay, so in this way, this lone pair, they are lone pair is shifting on the all carbon atoms of this benzene ring. So in that way, as that one is changing its room, its space, its delocalization occurs for this negative charge. So due to this delocalization, it attains more and more stability. So here we can say benzyl carbanion is more stable due to the delocalizations, due to the effect of resonance. So here if we will increase the phenyl ring on this CH2, if two phenyl groups are present, then again this stability is getting uh, okay, stability increases with increasing number of resonating structure. Okay, so here this one C6H5 CH2, this is they do show this is more stable. After that, diphenyl benzyl anion is least stable, and triphenyl benzyl anion is the least stable as per the uh, reference. Okay, so the next slide, conjugation of the unshared pair with an unsaturated bond. Okay, so the as we have seen that negative charge, as negative charge is getting more space for delocalization, that one is getting happy, and as negative charge is getting more space for delocalization, that one is getting more stable. Here I have shown one more structure, that benzyl carbanion. We have seen that how benzyl carbanion, that one is shifting its negative charge from CH to minus to the different carbon atoms of the benzene ring. And now we will take another example of this one. So here is number 21 I have given. So this is another example of this carbanion, and here you can say, here this CH2 minus this carbanion, again this carbon is shifting in this benzene ring in conjugation with carbonyl group. So conjugation is increased over here. Okay, so here is 3 carbon double bond, one carbonyl group, and again 3 carbon double bond. So here this negative charge is getting shifted on different carbon atoms, and due to that one, this carbanion, this particular this structure is most stable. Okay, so that because of the resonance effect. Okay, so this is the example of the resonance effect. So we, as we provide more and more space or room for delocalization of this negative charge, that one is getting more stable. Okay, so the next one, so next factor is stabilization of carbanion by sulfur.